Okay, it's almost 45, sorry. So yeah, so it's our last talk today. So let me introduce our Professor Qing-Rui Wang. So he's from the Yao Center, Tsinghua, and he's the expert in the Fermionic SPT. So he has a lot of paper on how to construct fixed point wave function or Fermionic topological phase. And today he's going to introduce his recent work. How do we compute the staking rule for the Hooft anomaly of Fermionic topological phase? Let's welcome Professor Wang Qing-Rui.
Thank you very much for the introduction. It's my great honor to speak here at this wonderful conference. So today I was going to tell you the story about the stacking group structure of Hooft anomalies in Fermionic SPT phases and also anomalies. So this work is done with those gentlemen. So Xinyu Ren and Shang Jiangning, they are from the group of Zheng Tenggu at Chinese University of Hong Kong. Xinyu Ren is a graduate student, and Shang Jiangning was a postdoc. And another gentleman is Yang Qi from Fudan University, and most of the work about computation about complicated groups, such as some very complicated point group or space-like group are done by Yang Qi's code. Okay, so this is the outline. So at first, I'd like to introduce what is the notion of Hooft anomaly and what we mean is stacking group structure for this Hooft anomaly. And then I will give you two examples. One is 0 plus 1 dimensional anomaly, so it's a quantum mechanics. And we can ask whether this quantum mechanics with such a symmetry, which is Z2T, means that it's the time-Rosso symmetry with the group structure is just Z2. And we ask what is the anomaly for this Z2T symmetric quantum mechanics. And it is related to a 1 plus 1 dimensional Fermionic SPT state. And the final classification is actually Z8. This is the simple example. And the second example is 1 higher dimension. So it's a 1 plus 1 dimensional like a spin chain. And we ask, what is the anomaly for this system with a unitary Z2 symmetry? So previously it's a Z2T, now it's a unitary Z2. And it is related to a 2 plus 1 dimensional Fermionic SPT state that I will define later. And the classification is also Z8. And then later I will tell you how to generalize this result to arbitrary symmetry group. Okay. So let's go on. So what is Hooft anomaly? So Hooft anomaly is about quantum field theory with some global symmetry. For example, we have a path integral like that, and the degrees of freedom, we can choose it to be some scalar field phi, for example, and the path integral over phi with this action s. And now we impose a symmetry to this action, meaning that there is a transformation of this scalar field phi, and this G is a group element of this group G, and it acts on this phi to give you another phi. We call it phi G. And also the integration measure also should change, but for simplicity, we assume that it does not change under the symmetry group G. Okay, so that gives you a quantum field theory with a global symmetry capital G. Okay, now what we want to do is couple this global symmetry, global symmetry G to some background gauge field. So now we want to promote this global symmetry G to a local gauge symmetry. So we add a gauge field, and I call it A. Okay, so A is a gauge field. Now the integration is also integral this phi, and with some action that may be the minimal coupling of this A, gauge field A, and the scalar field phi. And the problem now is that this action, Z, which is a function of A, this action may not be gauge invariant under the gauge transformation of this A. So the difference between this ZAG and ZA is this factor. I call it Z anomaly. And that's the anomaly term. And this anomaly term may depend on both this A and the gauge transformation parameter G. Okay, so that's the problem. So why is the problem? The problem is that this Z anomaly is called anomaly polynomial. The problem is that we cannot integrate out A consistently. That's the problem. Why is the problem? That's because if we want to integrate out this A, what we integrate out is actually an equivalent class of this A, modulo the gauge transformations. So that means we want to integrate out over just a representative of this gauge field A. But the problem is that for different representative of this gauge field A, for example, A or AG, they are gauge equivalent, but they gives you different ZA. Therefore, it's not consistent. We cannot integrate out this orbit of this A. So that's the problem. And this problem is called Hooft anomaly. Okay, now the problem is that why it is important, why we care about it and want to classify it. The importance is that Hooft anomaly is an obstruction to promote the global symmetry to local gauge symmetry, and it is invariant under RG flow. Usually invariant under RG flow. If we construct some state that is discretized, therefore, there is some rigidity there, then it's invariant under RG flow. So it constrains some quantum field from the UV to the IR. For example, a famous example is the Lipschitz-Matisse theorem in condensed matter. Well, it states like that. So, for example, we have a spin chain, spin 1/2 spin chain. And for this spin chain, we impose two different kinds of symmetry. One is a lattice translational symmetry. We can translate it by a lattice constant, and the Hamiltonian is invariant. Another symmetry is this SU2 spin rotational symmetry. We have two different symmetries. And the problem is that in the UV, we have a Hooft anomaly between these two symmetries. One is the lattice translation. It is a space symmetry, not an internal symmetry. Another is SU2 spin rotational. It's an internal symmetry. There is a mixed Hooft anomaly between these two symmetries. And therefore, we know that under RG, the IR should also have this Hooft anomaly. And if the IR have this Hooft anomaly, then we know that the IR quantum field theory cannot be trivially gapped, meaning that it can either gap this, or we have many different degenerate ground state, or it can be spontaneous symmetry breaking to break, for example, this lattice translation symmetry, or break this SU2 symmetry. So that's the story, importance of Hooft anomaly. But this Hooft anomaly story is ultimately linked to the problem of SPD phases that introduced by Gu and Wang in 2009. It is like this. So we have this anomaly polynomial, which is the difference between ZAG and ZA. The A is transformed under gauge transformation to AG, and the partition function have a difference. And this one can be drawn like that. So we have M is a d-dimensional manifold, M prime is another n-dimensional manifold, and we have gauge field A on the left-hand side, but we have gauge field A prime on the right-hand side. And these two are connected by a manifold with one higher dimension. And this manifold with one higher dimension, we can call it this Z anomaly. So this Z anomaly can be considered as like this a synonym, which, or more precisely, is a bordism from this M manifold to this M prime manifold. And this Z anomaly is a partition function associated with this bordism manifold. Okay? So therefore, it is associated with manifold in one higher dimension. And also this one is a U1 phase vector. Since it's a U1 phase vector, so that means the partition function associated with one higher dimension manifold should be a one-dimensional quantum field theory. Therefore, it goes to the theory of SPD state, symmetry-protected topological phase. So symmetry-protected topological phase, by definition, it is a gapped phase. So the ground state it has a unique ground state, and it is invertible in the sense that the partition function is only a U1 phase. So it can be, we can do inverse for this system, and it also has a group symmetry G. So it's a symmetry protected. If we forget about the symmetry, then this SPD phase can be trivial, can be connected to the vector. But if we insist this G symmetry, then there may be different types of SPD states. So that's the correspondence. So on the boundary, we have a quantum field theory with Hooft anomaly in d dimension, and in the bulk, it is an invertible gapped state with G symmetry in one higher dimension. And so that's the correspondence. So the problem of classifying d-dimensional Hooft anomaly with symmetry group G can be then promote to another question that is, in some sense, answered in Connor's method. That is the classification of d plus one dimensional SPD state with symmetry group G. Now, since we understand the relation between Hooft anomaly and SPD phases, then we ask, what is the stacking structure for this anomaly or SPD? So for example, we consider we have two quantum field theories, and then we just tensor these two quantum field theories together. Tensor means that we put the degrees of freedom together. So the Hilbert space of the total system means that's the tensor product of the Hilbert space of the individual ones. And also the Hamiltonian, just put them together, or the action may add them together. So this gives us a partition function that is just the product of Z quantum field theory 1 and Z quantum field theory 2. And this Z is, if we consider the SPD set, it's just a U1 phase vector. So this U1 phase vector multiplied together, they can form an abelian group. So therefore, that's the abelian group structure for bosonic SPD. It's very simple. We just put these two U1 phase vector of the partition function together, we obtain the abelian group structure. So that's it. But the problem is that so that's the picture. We just put two different SPD together and obtain another SPD and ask what is the total SPD when we stack two different SPD. And the problem is that for bosonic one, it's very simple. Just put them together and multiply this partition function together. But for fermionic one, the structure becomes more and more complicated if we want to go higher and higher dimensions. Okay, then I will tell you why it is complicated by simply considering this example, a 0 plus 1 dimensional Z2T and also invariant quantum mechanics, and ask what is the classification of Hooft anomalies for this quantum mechanics system. Okay, so that's the goal. So the example is that we have a system with symmetry that is the product of fermion parity. So we are now in a fermionic system. Just for bosonic system, the stacking structure is very simple. But for fermionic system, we always have this Z2 symmetry, which corresponds to the fermion parity or the conservation of fermion numbers, mod 2. And we also add an additional symmetry that is the time lossy symmetry, Z2T. So this is the symmetry. And now if we consider a problem that is simpler, which means it is a free fermion system, we just impose the condition that the Hamiltonian can be only a two-body interaction. So it's a free fermion system. And for free fermion system, we can just diagonalize the Hamiltonian very easily. And then people found that in the classification of topological instrument and superconductor, there is a tenfold way. And this corresponds to one of the tenfold way classification. And you find that in 1 plus 1D, this is classified by Z. So it is an integer. That means we have infinite number of Hooft anomalies associated with this symmetry group, Z2F times Z2T. But this is for free fermion system or two-body interaction system. The problem is that what if we introduce more and more complicated interactions, such as four-body interaction? So adding four-body interaction will reduce this classification Z into another classification. The final result is Z8. So I will show you the simple ideas of this Witkowski and Kitaev paper in 2009. So the setup they have is like this. So this free fermion Z classification corresponds to we call a Kitaev chain. So this is a Kitaev chain. Kitaev chain is a P-wave superconductor in 1 plus 1 dimensional, and it just corresponds to we have different we have many Majorana fermions. Each dot represents Majorana fermion, and or a pair of Majorana fermions is a complex. But the problem is that we just pair these Majorana fermions that is between different sites. It's not inside the site. It's between different neighboring sites. Therefore, we construct this Hamiltonian and also Guangxi wave function. This is called a K-type chain. And for this K-type chain, we can stack as many as the number can increase. You can add an arbitrary number of K-type chains together, and you can add arbitrary two-body interaction, and you will find that it is always stable. So therefore, the classification is Z. So you can stack n layers of K-type chain, and they are stable. So the classification is Z. The problem is that if we add four-body interaction into the system, for example, if K is 8, and we add the interaction for this boundary Majorana fermion, and they find out that, Pitkowski and Kitaev find out that this Hamiltonian, this W, with very complicated four-body interaction, will drive this X state into a trivial product state. So that means it is a gapped Hamiltonian, both in the bulk and on the boundary. So it's a trivial SPT. And the trivial can be seen from two different ways. One is from the bulk. So the bulk is an SPT state. But now, with 8 copies of K-type chain, this bulk becomes trivial. And another is from the boundary. The boundary, initially, it is 8 copies of Majorana fermion. But 8 copies of Majorana fermion is driven to a product state, or a single gapped state with single ground state that is given by this Hamiltonian. So that means it is gapped out. The edge is gapped out. And the gapped out edge is a 0 plus 1 dimensional quantum theory of quantum mechanics that is without any anomaly, because the symmetry can act on the ground state, the unique ground state trivially. Therefore, there is no Hooft anomaly for this K equal to 8 case. So that's the argument. The time-reversal symmetry will act on this Majorana fermion trivially. So basically, it acts on the left edge, trivially acts on the right edge by minus sign. So there is a time-reversal action on this. And you can show this W will stack this time-reversal symmetry. And this one, if we only consider the bulk, it is a 1 plus 1 dimensional fermion SPD. And we can ask what is the partition function for this SPD, or the anomaly polynomial for this. And the anomaly polynomial is given by this ABK invariance. And basically, Kapustin and his friends proposed that we can use this two-dimensional bordism group to also classify this fermion SPD state or the Hooft anomalies. And these two correspond to, it is a 1 plus 1 dimensional system. So it's two-dimensional space-time. And this P minus means that it is a spin structure that is related to time reversal square is plus 1. And therefore, they just compute this bordism group and find that it is Z8. And this Z8 can be used, this ABK invariant can be used to write down the partition function of this Z8. For example, this K can go from 1 to 8. And one of the state that is known in the bosonic case is the K equal to 4 case. If K equals 4, this partition function, this ABK invariant will become this W1 square. W1 is the first differentiating class. And therefore, it reduced to the famous Houdan chain. So therefore, it is a bosonic SPD state protected by this Z2T symmetry, no, without Z2F symmetry. So therefore, it's a bosonic system. And now, this one is the partition function for 1 plus 1 dimensional SPD with Z2T symmetry. And we can also consider this Z8 classification from the 0 plus 1 dimensional anomaly. So previously, we are considering the partition function of that. And now we're considering the boundary. It's a 0 plus 1 dimensional quantum mechanics system. We can just ask, what is the Z2T anomaly of this quantum mechanics? So it's a very simple question. So it's a 0 plus 1 dimensional quantum mechanics with the symmetry of Z to F, and also from parity symmetry and Z to T, and also symmetry. And people know that the Hooft anomaly in 0 plus 1D in quantum mechanics is actually associated with the projective representation of the symmetry group, at least in the bosonic case. But in the fermionic case, it's similar. For example, we only consider this is the generator. P is the generator of Z to F, and T is the generator of Z to T. And they just, P square and T square is 1, and P and T, they commute. So that's the Hooft structure. But now, when we consider this K equal to 2 case, what we find that on the boundary, there are 2 monofermions. And 2 monofermions can be composed into 1 complex fermion. And therefore, this 1 complex fermion can be empty or occupied. And this empty and occupied state is degenerate. And therefore, you find that this P and T symmetry is realized on this system as P times T is minus T times P. They anti-commute. Therefore, it is a projective representation of this derive product. And similarly, if we consider this K equal to 4 case, which is the Howden chain case, and therefore we have 4 monofermions on the boundary, and 4 monofermion becomes 2 complex. And we can also add an additional symmetry to break this 4 degeneracy into 2 degeneracy, but with both of these 2 symmetry to be two ground state to be fermion parity even. So it's a bosonic state. And this bosonic state is realized by this symmetry. So T becomes the Fermi stability action, and P, since it's bosonic, so P is always 1. So therefore, we find that T square is minus 1 for simply for Fermi degeneracy. Therefore, we realize that this K equal to 2 and K equal to 4, both of them correspond to the projective representation of this Z2 times Z2. Also, here, this problem is actually a supersymmetric quantum mechanics because you find that this P is fermion parity. The T and fermion parity anti-commute means that this T action will actually change the fermion parity number by 1. So it will map the bosonic system to a fermionic system. It will map this. So just like a Q operator in supersymmetry. So that's the classification from both the bulk and the boundary. And now we want to go further. This is the simple example for Z from T. We want to ask what is the classification for arbitrary symmetry group G. So this goes to general Fermion SPD classification or construction. And in this supercohomology construction, we just put like this. So we have a wave function. So the wave function is like this. So we have a one-dimensional chain. And for this one-dimensional chain, on each vertex or on each side, we put a group element here. This is G0, G1, G2, both belong to, all of them belong to capital G. And they span the Hilbert space. So the dimension of the Hilbert space is the order of group G. And then we put a complex fermion. So this on the link, we put a complex fermion mode. This is C01 with also a label of group element G. And then we put this K-type chain. So we have 3 layers. One is the bosonic layer. Another is a complex fermion layer. The third layer is the K-type chain layer. So we put all these 3 layers together, we obtain this triple, this N0, N1, and nu2. N0 equals 0 or 1, depending on whether you have a K-type chain or not. And this N1 is a 1 chain that indicates whether this link is occupied by a complex fermion or not. And finally, this nu2 is a phase vector. This phase vector is associated with the F move that I will tell you later. So these are the 3 layers of Fermion SPD constructions. And for example, if we consider Z2T, we have 8 different constructions because each of this H or this C2, C1 have a Z2 classification. Therefore, we have in total 8 different choices. So that corresponds to the Z8 classification. But in general, how can we do the stacking structure? So how do we obtain the stacking group structure of the Fermion SPD state with arbitrary group G? So we just stack two fermion SPD together like that. So this is a fermion SPD state. And there is another fermion SPD state. And we just put them together to obtain the total one. But the total one is that we want to obtain this capital N0 and N1. But the problem is that from these two K-type chain, two fermion SPD state to this one fermion SPD state, we have to project out something. It is not invertible anymore. So what we do is that we do not project out this Hilbert space. We just put all others into a trivial product state. So we add some product state on the right hand and on the left hand side of this equation and make this P to be an invertible process. It's an invertible transformation. Actually, it's a unitary transformation. So it is a fermionic symmetric local unitary transformation. So symmetric means that it also preserves the symmetry of G. Okay. So that's the construction. And using this construction, we can project these two copies of fermion SPD state into one fermion SPD state and one trivial product state. And using that, we can do the calculation. For example, when we stack two K-type chain together, like this, so we have a K-type chain that here, and we have another K-type chain, and we want to put them together and do some fermionic local unitary to remove the K-type chain totally. And the removing procedure can be done by writing down the explicit local unitary operators. And for example, we can initially the K-type chain, the Marana chain is pairing like that, but now we can pairing them vertically, and then finally we obtain this result. So N0 and N1. So N0 is the K-type chain data for the first chain. N0 prime is the data for the second. So when they put together, if both of them equal to 1, then we got no K-type chain when we put them together. So it's just a simple addition. But the problem is that the N1 declaration, N1 is related to the complex fermion declaration. When we stack two complex fermion declaration together, we should add them together. But the problem is that the K-type chain will also contribute to this N1 data. So it's S1 cup N1 and N1 prime. That means if both of them are occupied by a K-type chain, when we stack them together, and if this S1 is related to the anti-unity symmetry, we'll find that this N1 becomes non-trivial. So two K-type chain declaration will become one complex fermion declaration. So it's like a twisted version of the stack. And similarly, we can understand what is the stacking of nu2. Nu2 is related to the F symbol of this 1 plus 1 dimensional system. So it's much simpler than the F move for a fusion category. So the F move is like this. So we have 3 dots and 2 links. And then we do an RG to make it to be 2 sides and 1 edge. So that's the F move. And we require that this F move preserve all the symmetry that we require. And also, yeah, it's like we just make all the second layer trivial. So we move all the non-trivial data from the second layer to the first layer. And the first layer then can be viewed as the total system. Yeah. Yeah. It's done it. We stack this stack. Yeah, this is the F move. This only for one layer. Yeah, I will tell you later. So that's only for a classification of SPD. We're not talking about the stacking of that. Yeah. So that's for one layer, and that's the symmetry action also for one layer. And they should satisfy some pentagon equation, but the simplified version of pentagon equation like this. And that's your question. So we now add 2 layers of Fermionic SPD. And for this 2 layer, we can do F move for both of them. So there is an F tensor with F1. Okay? And then we can do projection for on the left-hand side and on the right-hand side. And the bottom edge is that we have a total F move for this combined system. And we asked, we should ask this square to commute. Therefore, we have this relation. And from this relation, we can recover what is the F total for the total system F move. And we can read out what is the Newton data for the total system. So that's the procedure we do. And finally, we obtain the stacking rule like that. So we have a Fermionic SPD labeled by these 3 data and another SPD. When we stack them together, we obtain a total one. And the total one and these 2 are related by these equations. So N2 is, N0 is just an addition of this individual N2, N0. And N1 is the addition of the individual one and also a twisted one by N0. And for nu2, it's the product or addition of this nu2, but with additional twist from both N1 and N0. So this is from N1 and this from N0. It's twisted by both of the 2 layers previously. Okay, if we use this data, and we can calculate the previous example of Z2T, and it indeed will give us the Z8 classification. And this result also agree with some other results from using other methods different from an SPD. No. They just use, I don't know, some arguments to understand what is the representation of this symmetry group, like more like a boundary analysis. We also obtain the same result. So that's the 0 plus 1 dimensional example anomalies, 1 plus 1 dimensional from an SPD. And now I will move on to 1 higher dimension. So it's a 1 plus 1 dimensional anomaly. It's a 1 plus 1 dimensional quantum field theory with Z2 symmetry, but this Z2 is a unitary Z2. And also it's related to a 2 plus 1 dimensional Fermionic SPD state in 2 plus 1B. And this example was first studied in this paper, Gu and Levin paper, 10 years ago. And they consider the symmetry to be fermion parity and heterodyne. Sorry, I should. This is not heterodyne. It's a unitary Z2 symmetry. So it's a Z2F times a unitary Z2. So the setup of them is that they consider K copies of P plus IP and P minus IP superconductors. So it's like this. So we have 2 layers. The first layer is a P plus 1 IP chiral superconductor with spin up. And for spin down, we have a P minus IP such that the chiral central charge just vanishes. Okay, so it can map to a trivial product state if we forget about the symmetry. Okay, so that's the setup. And we ask what is the symmetry Z2 acting on this one. So the symmetry acting is just the poly-Z act. So it acts on the first layer, spin up trivially, but acting on the fermion of the second layer, spin down fermion by a minus sign. So that's the Z2 action. And on the boundary, since it's a P plus IP superconductor, so on the boundary, there will be K copies. So that's the K copies of P plus IP and P minus IP. So on the boundary, it will be K copies of chiral monomer mode on the top, and also K copies of chiral monomer modes on the bottom. We have 2K monomer modes. Half of them are left moving, half of them are right moving. And then we want to ask the question whether this boundary is anomalous or not when we increase this K. Or in other words, whether the bulk can be trivial when we increase this K. So we can answer this question in 2 different ways, one from the bulk, another from the boundary. So let's first consider from the bulk approach. The final result is Z8, also Z8. The bulk approach goes like that. Since we have P copies of P plus IP and P minus IP, we can we can simply gauge the symmetry, Z2 times Z2 symmetry. So previously we have two Z2 symmetry, two unitary Z2, Z2F and Z2. But now we can change it into Z2 up and Z2 down. Z2 up is the symmetry for the first layer, Z2 down is the symmetry for the second layer. And we can gauge this unitary Z2 times Z2 symmetry of this P plus IP or P minus IP superconductor. And here we can use the Kitaev's famous Z16 fold way and ask what we get after we gauging the symmetry. The answer is that for k equals to 0, gauging this symmetry, gauging this 0 copies of P plus IP or P minus IP will give us just toric, the simple toric. And k equal to A will give us another toric, also with 4 different types of anions. But the problem is that except this trivial anion, all the 3 non-trivial anions are all fermions. They are all fermion toric. Okay, so there are 2 different types of anions in this system. The problem is that k equals 0 and k equals to A, they found a way to identify them. So that's the k equal to 0 case. You have this many anions in this system, this gauge system. And for nu equal to A, you have also this many anions. But you can find a map between these two such that all the reading data and fusion data are the same for the 2 sets of anions. So therefore, this nu or k equal to 0 and k equal to A should be identified since they gives you the same bound. Yeah. So we have 16 anions. And it's just a permutation of these 16 anions, but they are the same. Therefore, all the modular data are the same for this. All the categories are just the same. The modular tensor categories of these 2 cases are the same. So therefore, you should say that this k equals 0 and k equals A should belong to the same phase. So that's the gauge phase. And before gauging is an SPT. So therefore, before gauging, you should also identify them as the same SPT since they gauge to the same gauge state or any of them. So therefore, we obtain this Z8 classification. That's from the bulk point of view. And from the boundary point of view, it's like this. So on the boundary, we have k copies of left-moving and right-moving Wagner fermions. And we can just bosonize this to a system like that. So phi is a boson field with k components. For example, k equal to A. And Kij is a matrix. And then we ask whether we can add some symmetry preserved term such that we can just get out this edge. And actually they found it is true. So they use this backscattering term like that to gap out this X state if k equal to 8. And they find explicitly what is lambda. Lambda is a gapping vector to gap out this system. And they find that for k smaller than 8, it is not possible. We cannot gap this out. But for k equal to 8, we can add this term to fully gap out the X state. Therefore, we obtain a 1 plus 1 dimensional quantum field theory that is gapped and with a unique ground state. Therefore, it should not have any Hooft anomaly. So the Hooft anomaly for this system is also Z10. So therefore, we obtain the same result from the bulk and from the boundary. Now we want to generalize this result to even more complicated symmetry. For example, we ask whether we can ask what is this G can be general, and also it can be heterogeneous or unitary, and also we can have a symmetry extension from this G and the fermion parity Z to F. So there are more and more complicated symmetry groups. Yeah. I think there's no easy way to say that, but The W domain 1 is similar to our construction, and I will tell you how we obtain the same result using our construction. Yeah. Yeah, it's far from, it's far from obvious. Just this P plus IP do not have fixed point wave function. It needs infinite number of degrees of freedom, so we do not. So for arbitrary symmetry group, we just use similar to 1 plus 1D. We have a 2 plus 1 dimensional classification from the SPD using group supercohomology. They have also 3 layers of data, one from the declaration of data chain, another from complex fermion, the third is from the bosonic U1 phase vector. So the ground state wave function is like a superposition of all these possible states. And this green line means that there is a data chain in this wave function, and this dot means that there is a complex fermion inside this triangle. And we do a superposition of all this state and ask what is the relation of this wave function. And this wave function should satisfy the famous F move. And now this F move is the F move for superposition category, and even more fanciful one with some Q-type anions, Q-type objects. That means the endomorphism of this object is the different algebra. And it satisfies this F move. So we have from one triangulation to another triangulation, we can relate them by a symmetric local unitary transformation. And also this F move should satisfy the pentagon equation, but now it's a super pentagon equation with some additional sign twist. And this twist can not only be plus minus 1 because of the complex fermion, but can also be plus minus I because of this theta chain. That chain can give you plus minus I dependence of this pentagon. It's more and more complicated if we consider the both theta chain and complex domain. So I phase is like, so when we say complex amount of fermion, we have a parent term, which is amount of fermion, like I gamma 1, gamma 2 equals to plus minus 1 or minus 1. Right? So therefore, it means gamma 1 and gamma 2. So gamma 1 equals to I gamma 2. That. So you have a different hopping of the amount of fermion will gives you not only plus minus 1, but also plus minus I. It's like a hopping of amount of. The hopping of complex fermion will give you plus minus 1, but monofermion is half complex fermion will give you half minus 1. So therefore, we can do the similar thing. We just stack 2 layers of 2-dimensional fermion SPD, and then that's the two layer. There's another 2 layer. They are related by an F move, so F tensor F. And then we do a projection. We project 2 layers of fermion SPD into 1 layer, and another layer is put into the product state. And therefore, we ask what is the total F move for this total combined system. And then we can read out all the data we needed to construct this stacking structure. So the stacking group structure is like that. So I omit all the details, but the final result, I can show you the final result. The final result is like this. So we have 3 layers, 3 different layers of classification, N1, N2, and U3. And 2 layers of SPD are put together to obtain the total one. The total one is related to the individual one by this N1 is just the addition. And N2 is twisted by this N1, by this term. The N1 have N1 prime, and also S1 term that is related to anti-unitary. And the most complicated one is the bosonic one. The bosonic nu3 is related to nu3 and nu3 prime by a phase vector. And this phase vector will split into epsilon 3 and theta 3. And now I show you what is the result. This slide only, I only want to tell you how complicated it can be. Right? So this epsilon 3 is mod 2 numbers. It can be only 0 and 1. It's a phase vector. It's a sign. And this theta 3 It's not just a sign. It can be 1/2, which is a sign. And 1/4 is plus minus I. And even more complicated, if there are anti-unit symmetry, it can be 1/8. It's more fractionalized than we expected. And this 1/8 is related to the Z8 classification. That means we can at most have a Z8 classification. We cannot have. So we can extend 2 times, but we cannot extend a third. Therefore, that's the meaning of this phase. For the simpler case, like I think without S1, I computed it by hand. And with S1, then we find it too complicated to do it by hand. Then we use a computer to solve the equation and find this result. And find this result, and we then ask whether we can write it down as some higher couple. Then we try that and find this. This is enough. Okay, so this is our result. And I think that's the first case that we actually computed this 1 + 1 dimensional Hooft anomaly of Fermionic system for arbitrary symmetry group. And there is a comparison with other results, for example, from spin bordism. So Kapstin proposed the spin bordism classification for Fermionic SPT, and later Braunfeld and Morgan, they just used some tools, they just computed some spectral sequence in algebraic topology, and they found the result for Z2F times G. And this is the direct product of these two groups. And also this G should not contain Hammurabi symmetry. Therefore, they have this result. But this result is much simpler than our result because we can just simply set omega2 and S1 to 0. So if we set these two to be 0 and all the complicated terms, so this theta 3 will have 4 terms. And the first term is just the John Morgan's result. So that term is this one. For example, this 1/4 and AB square. And AB square is our result like this. It's 1/4 and N1 have N1 prime, N1 prime. This is A, this is 2B. Okay, so that's their result. And if we add additional omega2 is related to the group extension, and also include this S1. S1 is the Hammurabi symmetry, then the problem becomes more and more complicated. And even the mixed term of this omega2 and S1, the fourth, they become more and more complicated in these cases. They can compute case by case. They can compute some group case by case. But if you want to obtain a formula for arbitrary group, then we have to know all the differentials in the spectral sequence, and which is very complicated. So basically, we are giving a physical derivation of these differentials in the spectral sequence. Yeah, there's 3 + 1D with also a product of these two groups and also union. Our paper, my paper with Zheng Cheng also have this in our appendix, but we do not summarize into a formula. We just calculate by computer to compute the Hermione normal form of some very large matrix and obtain the result. They compute it also using SAGE. You can see this beyond mathematical. And they summarize the result into a formula with maybe 4 pages long. Yeah, these two. Another for 3 + 1D. And now we are trying to promote this result for 3 + 1D with omega2 and S3. Problem become more and more complicated. So let's go to examples. So using these formulas, we can construct the examples of Fermionic SPT or 1 + 1D Hooft anomalies. So the first example is that GF is just finite Abelian unitary symmetry. It's just like the derived product of many Zn. So for this group, and we find that the stacking group structure of this Fermionic SPD or Hooft anomaly is also a direct product of several groups. So the first group, A, is protected by this Z2F, this permanent parity part. And this B is related to one of this ZNI symmetry. And this C is protected by two of ZN. And this D is related by three of them. Okay? And the final result is like that. So A can be Zm or Zm over 2. So M is N0 over 2. So A is this group. And B is also some group that depends on whether Ni is odd or even, and whether Ni mod 4 is 2 or 0, and similar for C and D. That's the final result. And this Nijk means the largest common divisor of Ni, Nj, and Nk, and similar for this Ij. So that's the final result. And this final result is also obtained by Qing-Rui Wang and Zheng Hu from another approach. They use gradient statistics of this 2 plus 1 dimensional system, and they obtain exactly the same result. Now we can use our results to recover them. And here is some examples. So this example, you just choose different this ZNI, you obtain the final result. That's one of the examples. Another example is more complicated. That is from the some condensed matter system with lattice symmetry. For example, when we consider 2 plus 1 dimensional Fermionic SPD, and usually we are putting these things on the lattice, regular lattice. And a regular lattice can have point group symmetry or wallpaper group or space group symmetry. And for this, all this 2 plus 1 dimensional wallpaper group symmetry, we can calculate the classification. For example, this is done not by hand, it's by code. Using our formulas, and Yang Qi write a code, and using his code, we can calculate all the obstruction functions and all the extension problems, and finally obtain the group classification. For example, for the P1 space group, we have Mahana chain declaration, which is classified Z2 square, and complex fermion is Z2, and boson is just Z1, so we do not have them. Therefore, the final classification is just the direct product of these two. But for P2 group, we have Z2 to the third, and Z2 to the fourth, and this Z2 to the fourth. But the final classification is Z4 times Z8 cubed. So this Z8 means that we have 3 different copies of Z2, Z2, and Z2. This extended to a Z8. Okay? And finally, this is 4. So we left out with a Z2 here and Z2 here. And these Z2 are extended to a Z4 symmetry. So therefore, we obtain this classification. So it's case by case. So we do not have a simple answer why for this group we have an extension, for other group we do not have an extension. But using our formulas, we can derive all the result. Okay, so that's the final result for our classification. So for the summary, I have shown you that a Hooft anomaly in D dimension is always associated with the SPD in one higher dimension, both for bosonic system and for fermionic system. And also, we have different layers of Fermionic SPD. And different layers of SPD are mixed together when we ask the question of stacking them. And the stacking group law of this Fermionic SPD are obtained in 0 plus 1D, 2 plus 1 plus 1D, and 2 plus 1. For 3 plus 1D, we have result for direct product state, but we do not include omega 2 and S1 in unitary and group extension. So the future work may be, so for example, how do we write down an explicit quantum field theory on the boundary to realize this Hooft anomalies? So it matches our classification result, or how to generalize into even higher dimensions. That's the part. Thank you.
Any questions?
Nice talk. So I want to know, do you know that there is a categorical approach to categorify fermionic SPD? One of them is using the minimum extension in 2 plus 1D case. So as far as I know, for the fermionic group, which is given by Z2 times bosonic part group, arbitrary G. There is a lot of results in that direction. We have been worked out by many mathematicians. So there are some formal rigorous result. So I want to know, have you compared your result with those?
I think they have established some framework for that, but when I want to compare with some examples, I think the only one I found is from the spin bordism result. They have computed some examples and formulas. But for the categorical sense, I did not find examples and formulas like ours, so it's hard to compare. Right after way to calculate. But yeah.
Well, perhaps I'm not referring to them. Maybe I know there's some work by Dmitry Niksik. He has some a way to, I think in that special case, he can prove that this group can be written as some kind of combination of higher group homologies or something.
Yeah, I think it's for our case, it's also can be associated with some generalized cohomology. It's so spin bordism is also a generalized cohomology.
Yeah,
so we can.
I know, right.
Two. I see.
Any other question? Yeah, in that.
Outlook. So do you have a anomaly polynomial for this kind of thing that you expect? Because you are looking for a QFT with such anomalies.
Yeah, the anomaly polynomial is like to ask the partition function of this Fermionic SPT, and basically we find it's very hard to write down explicitly for arbitrary group because of we have to add more and more data like spin structure. We need to include spin structure into the partition function. It depends on the spin structure. But in our case, we are working on the space manifold. Therefore, we can get rid of the spin structure. And it seems to be much simpler than the space-time picture because we have one lower dimension.
Do you have an example with like anomaly polynomial written in some differential forms or as a cocycles?
For some Zn times Zn this group, I think people know the result. It's also like a cup product or higher cup product. Yeah.
So in this work, did you work out with the Z2F with G and with non-trivial omega 2 and S1? You have formula.
Yeah, I have formula. Yeah. So
basically.
Yeah, so this is the mixture term for both omega 2 and S1.
I see. Basically, if I just consider this some SPT is non-trivial.
Yes. Yeah. For example, Z4TF, it's like T square equal -1. The T square equal to the Fermion parity. And we can use in these formulas to calculate this example. We agree with spin bordism.
That's very impressive. So, another question is for the Z2T, which is anti-unitary.
Yeah.
So are there difference between Z2, unitary Z2 approach?
Yeah. So for example, if you set S1 to be 0, then we do not have this term. Certain vanishes. So they are very, very different. And if you use unitary Z2 or anti-unitary Z2, you obtain totally different result.
Hello. Thank you for a nice talk. And I'm just out of curiosity, have people studied or can we build of a fermionic gapless or intrinsically gapless SPT system and classify them and
yeah,
like stacking them.
Yeah, but I'm not an expert on that direction. I know there are some results, but it seems that they are using some construction, but not the full classification is still unknown. Yeah.
I see. Sense.
So if there's no further question, let's send Professor Wang Qing-Rui again.